So welcome to the Picture Language Seminar. We're very pleased today to have Madelyn Cain. Maddie was an undergraduate at MIT, student of Yusha Lukin at Harvard, and will be going next fall to Google in Santa Barbara. So we're looking forward to hearing your talk about the fault-tolerant error correction. The floor is yours, Maddie.
Oh, thank you so much. So yeah, as Arthur said, my name is Maddie, and today I'm going to be talking about low overhead fault-tolerant for universal computation. Or in other words, how do we reduce the practical overhead of quantum error? So a real frontier in quantum information science right now is building more new platforms for quantum computation. And there are many platforms that are being explored right now, such as superconducting qubits, trap ions, and neutral atoms. And for these devices that we have today, the state-of-the-art gate error rates hovered around 10 to the minus 2 to 10 to the minus 3. Some of those audio is not so great. People online let me know if they're so in the platforms we have today, gate error rates are roughly 10 to the minus 2 to 10 to the minus 3. And the ultimate goal, of course, is to scale up these platforms in the future and use them to realize kind of large-scale applications of quantum computers. So this ranges everywhere from cryptography to understanding quantum mechanics itself. And because these large-scale applications are so complex, they require billions of operations. And as a result, the error rates that we need for operations actually hover around 10 to the minus 10 and below. And so there's a significant gap between these two numbers. And as a result, suppressing errors is one of the central challenges in quantum computation. And quantum error correction is really the only known realistic route to suppress gate errors to the levels that we need for large-scale algorithms. We don't expect to be able to achieve these numbers in the physical devices that we have. So because of this challenge, initially people thought quantum error correction and therefore quantum computation in general would actually just be fundamentally impossible. And this stems from the fact that it works quite differently than classical error correction. So in classical error correction, we encode redundancy by duplicating information. You can think of a repetition code, for example. But in quantum error correction, we have a conceptual challenge, which is that we can't copy quantum information. We can't just redundantly encode copies of our quantum state due to the no-cloning theorem. And so it was really a theoretical breakthrough that actually showed that we can correct errors in quantum computation. And the basic idea is to use entanglement to store information non-locally to encode a logical qubit in many physical qubits itself. And this non-locality makes it hard for individual local physical errors to kind of corrupt our logical information. Then we will use local operators called stabilizers in order to detect and correct errors. So I know there's probably a wide variety of backgrounds in the audience, so please ask questions. I will try and make this accessible to people from different fields. And to do this, I'll start by explaining a simple example of error correction, which is the surface code. The surface code you can think of as a product of two repetition codes. It basically encodes a logical qubit into an array of physical qubits in a two-dimensional array. And the size of the array is called the code distance d. And roughly you can think of it as a metric of how many errors we can detect and correct. So to see why it's a product of two repetition codes, we'll define our stabilizer operators, which we'll use to detect and correct errors. So we have the Z stabilizers, whose job it is to detect Z errors. And X stabilizers should detect Z errors, and Z stabilizer's job is to detect X errors. And this will give us the ability to detect the different types of errors that we have in a quantum device. Now we'll define our error-free state as having all of our stabilizers equal to +1. Then when an error occurs, say an X error on this physical qubit, our stabilizers which anti-commute with this error will then flip to -1, such as these two Z stabilizers right here. So this gives us information that we need to be able to go in and correct this error. And in general, we can have complex patterns of errors that occur. So we'll use a classical algorithm called a decoding algorithm, whose job it is to take in these stabilizer measurements and infer what error occurred so we can undo it. Now, I would say the most important theorem in quantum error correction is that of the threshold theorem. This basically says that I can exponentially reduce the probability that I have an error occur in my logical qubit as I increase my code distance d, or really the size of the code itself. And this will happen as long as my physical error rate p is below the threshold error rate p threshold. Now, this threshold error rate for the surface code actually hovers at around 1%, which offers us an extremely realistic route to very, very low errors just by scaling our code distance. And this 1% number is very close to the error rates that we have in devices today. And so it was this advent of QEC that actually really allowed the field of quantum computing to take off. So let's talk about where quantum error correction is today. It's actually an extremely active field. There have been a ton of breakthroughs recently, and it's realizing quantum error correction experimentally. So all of these different platforms are exploring the best way to do error correction, and I just want to highlight a couple of the recent breakthroughs in this field. So actually one of them was done here at Harvard in the basement of LISA, where the Adam Murray team demonstrated logical algorithms on tens of logical qubits. A more recent one was actually done by the team at Google, which basically showed that they could be below threshold for encoding a surface code on their device. So super exciting. And I think things will only accelerate in the next few years. So current projections are that certain platforms will have the ability to have thousands to even tens of thousands of physical qubits, and the ability to run deeper and deeper circuits. And so the real question that we need to ask is, can we then take these devices and implement interesting and useful fault-tolerant algorithms? So, is there questions? So I think this is a super exciting moment for the field. Really trying to understand at what point will we be able to run useful quantum error correction. So here we show the resources that we are project to need for running these various interesting applications like factoring or quantum dynamics. And what you can see is that we actually have still a pretty big challenge ahead of us. So a lot of these applications actually require potentially millions of physical qubits and runtime that can span anywhere from minutes to years, which seems extremely formidable. But what I think is really exciting is that in the next few years, with high likelihood, experiments are going to start creeping onto the bottom left corner of this plot. And furthermore, based on the developments in quantum error correction theory, there's a lot of evidence that we can actually significantly move down the resource overhead of these applications. And so I would say bridging the gap between hardware and useful error correction is really kind of the key frontier. And that'll be the topic of my talk today, is progress in that direction. So let's talk a little bit of the challenges that we have when we think about scaling quantum error correction. So this resources really require from trying to ensure fault tolerance, basically that our operations are robust against noise. And we can see where this arises if we just even think of a single surface code. So say that I've done some operation and I want to correct errors. I need to measure my stabilizers in order to see what errors have happened. And the way I'm going to do this in practice is I'm going to bring in an extra qubit, and I am going to basically use a quantum circuit to map the value of that stabilizer on a particular stabilizer I want to measure onto that qubit. Here, using kind of noisy entangling gates that will basically measure this Pauli X stabilizer. Now, when I get out my measurement result, I might see that it's +1, indicating that no errors have occurred. And I might think it's great, but if I were then to go and measure my stabilizer again, I can see that it's slipped to -1. And you might think, oh, we've detected an error. But we haven't necessarily detected an error. Because of the fact that this measurement circuit is faulty itself, we could have also just had an error occur in this measurement circuit. So we don't know if we actually had an error occurred or if my measurement was just wrong. And in order to be sure, I need to repeat this process many times. And it turns out to know our stabilizers with really high accuracy, we actually need to repeat it on the order of the code distance times. And just for context, when we think of these really large scale algorithms, the code distance is roughly 30, which means that we have a significantly, a pretty long circuit that we have to run just to tell what our stabilizers are. The problem becomes even more intense when we start thinking about running a logical circuit. So we have a bunch of logic gates that we want to do, but if we want to detect errors after our circuit, at least naively, we should then extract all of our errors after each gate. And that means repeating this process of syndrome extraction or stabilizer measurements on the order of V times. This means that when we want to do a gate, the time it takes is more than an order of magnitude longer than the time it takes to just do a physical gate. And this is a major issue. But we want to really question these assumptions. So intuitively, this process basically is ensuring that each gate operation that we do is fault tolerant or robust on its own. And we're going to be trying to relax this requirement by considering the fault tolerance of our algorithm as a whole, rather than its individual components. So the result I'll show today is that if we satisfy a variety of assumptions that I'll kind of go into, but in particular, using a type of logic gate called transversal gates, as well as having kind of clean magic state inputs and assuming fast decoding, I'll go into all of these, we can actually reduce the syndrome extraction overhead from order of D to actually order of 1. And this will really be by developing new techniques to kind of consider the fault tolerance of the entire algorithm in its entirety. So the theoretical implications of this is that we really kind of gain a new understanding about what we minimally require for fault tolerance. And practically, it gives us a pretty big depth reduction that we need for fault tolerance on algorithms that can run these transversal gates that I mentioned. And this is actually super relevant for platforms such as the Atom Array here at Harvard. The key crucial element that I'll talk about is reconfigurability. So first, I'll actually start by talking about previous experiments that we did earlier this year that allowed us to really start asking these questions about fault tolerance. And then I'll go into how we can get this PVC overhead reduction. So let's start with the experimental work. So the reconfigurable atom array we have here at Harvard looks a little bit like this. And the basic idea is that we're going to store our qubits in the electronic state of a rubidium atom. So in particular, we'll be using the hyperfine ground states of the outermost valence electron of this atom. And the reason that we do this is that they're very robust. They have long coherence times of a couple seconds. Then, if we want to entangle our qubits, we will excite these ground states up to a highly excited Rydberg state and into atoms that are near each other. And in this Rydberg state, will interact into a gate. And in particular, they'll do the native gate in our platform, which is the CC gate. So this is the basic idea of how the platform works, but I want to highlight one key feature, which is that of reconfigurability. So in particular, we have the ability to pick up into atoms and rearrange them during the computation while maintaining coherence. And what this means is that we can do gates between any pair of atoms that we want just by moving them. Maybe even more importantly is that we can do this process in parallel. So we can pick up a group of atoms and move them all together. And as it turns out, this is actually extremely useful in the context of error correction. Yeah.
How fast is the process of moving the atom?
Great question. So the question was how fast is the movement of atoms? And the answer is that a couple hundred microseconds. Yeah. So for context, our gate time is a little less than a microsecond. So it is kind of a longer time scale, but the thing that makes this really possible is that our coherence time is really long compared to the movement time. Any other questions so far? So this ability to reconfigure atoms was actually originally demonstrated back in 2022. And so here's a video from that work. This circuit that you see with the atoms moving around is actually preparing a toric code state. So a toric code is just a surface code with periodic boundary conditions. And the atoms you see zooming around are actually ancilla qubits, which are going around and doing gates with our data qubits in our toric code in order to measure their stabilizers. So super important to be synchronative. And the nice thing is that this circuit is actually programmed by just a couple of classical controls, two voltages that are addressing the x and y positions of atoms that are moving. And so as a result, we really get parallel control over all these qubits with order of one classical controls. So this is useful not only in the context of syndrome extraction, it turns out to be also extremely useful for doing logic gates. And in particular, these gates I mentioned earlier are called transversal gates. So a transversal gate realizes a logical operation by applying the same operation to the physical qubits within the code block. So for example, if I wanted to entangle two logical qubits, say with a transversal CMOS, I will just directly interact these delocalized degrees of freedom by performing pairwise physical CMOS between the two code blocks in order to realize a logical operation. This has the benefit of not only being super simple, but also fault tolerant. So because we're not doing any sort of gates between qubits within a code block, we are also not spreading errors. Furthermore, it's done with single logical qubit control rather than single physical qubit control. So we can still use this order of one classical controls that we saw in the previous slide. So in effect, all of the physical qubits are receiving the same instruction and just acting like one big atom. So a simple circuit that we can run to test this transversal CMOS is just by preparing a logical bell pair between two surface codes. So in order to do this, we'll first prepare the codes in plus and zero by putting all the physical qubits in plus or zero, and then measuring respectively the Z or X stabilizers. So this projects us into an entangled state. Then we'll interlace the two code blocks and do a transversal CNOT operation in order to entangle them. And then finally, we will measure them out in whatever basis we're interested in probing. So we then wanted to see this threshold concept that I explained earlier. So we'll increase the code distance from 3 all the way to 7 and try and see that our entangling operation improves as we do this. So we then will measure out our qubits and compute the fidelity from the expectations of our logical operators in different bases. And what we see is that as we increase our surface code distance, our logical error rate indeed goes down. So it's consistent with being below threshold of the circuit. Now, crucial to having this result was a particular decoding technique that we developed during this project called correlated decoding. And the basic idea is that we'll be decoding the logical qubits in our algorithm jointly, taking in both of their stabilizer values. This will allow us to track various correlated errors between our different logical qubits that might have happened when we did an entangling gate between them. And it'll also be, as we'll see, kind of a crucial ingredient that allows us to reduce our syndrome extraction from order D to order 1. So let's get into how this works a bit more. But first, I want to say, after we did this experiment, there was actually a lot of criticism about the particular circuit that we ran. Oh, goodness. Okay. And so that is actually because our logical state preparation in the circuit was non-fault tolerant. Remember that we prepared logical plus by putting all our physical qubits in plus and then measured our Z stabilizers once. What this means is that although our X stabilizers are +1 at the beginning, so our physical qubits are in plus, our Z stabilizers are totally random. And because they're extracted with a noisy circuit, they are unreliable. What this means is that if we just took the state we had at this point in time and tried to put all our stabilizers back to +1 and fix all these errors, actually the resulting state is provably a mixture of product states. It's not really even entangled. And this is exactly due to this uncertainty in our Z stabilizers. Furthermore, to reconstruct the ideal logical state, we would need to measure our stabilizers D times in order to really learn these stabilizers. So the real question that we then asked is, do we even need to reconstruct the state? And the answer we found was no. When we're doing quantum computation, we don't care about necessarily reconstructing the many body state within a logical qubit. We care about the measurements we get on our output of our logical qubit. In particular, what we care is that we are sampling from the error-free joint logical measurement distribution that we would expect from our state. In this case, about state. So in particular, for this state, if we measure in the XZ or ZX basis, these logical operators are 50-50 random. And as a result, we can kind of trivially sample from their ideal distribution by just returning randomly ±1. We don't even need to decode. On the other hand, if we measure in the XX or ZZ basis, these operators are +1 in the ideal case. And as a result, we need to get them right. But it turns out that we will be able to accurately predict their values by doing this correlated decoding technique I mentioned before. So let me explain how this works. And also, please ask questions because this part can be a little confusing when you first see it. So let's consider predicting logical XX. So when we do this, we're first going to initialize our codes. And we'll prepare logical plus by putting our physical qubits in plus, which will, as a result, put our X logical in +1, and it'll put all of our X stabilizers in +1. We're going to then entangle our two code blocks using a transversal C0 operation. Now, the key point about a transversal operation is that it's going to propagate all the Pauli operators the exact same way on the physical level as will happen on the logical level. So an X Pauli will go from the control and be copied onto the target. What this means is now our logical X operators are entangled. And furthermore, so are our code stabilizers. So now each stabilizer product of X stabilizers between our two codes is reliably +1. Now, when we go and measure our qubits, we get crucially very reliable information about our stabilizer values. So it turns out that when we measure out all our data qubits, we gain a lot more reliable information than if we use some noisy circuit to measure these values. And this is because we'll basically directly reconstruct our stabilizer values from the measurements of the data qubits themselves. You can think of these measurements not. As a result, these reliable X stabilizer products are now +1. Sorry, they were +1, and now we gain that information reliably. What this means is that we can then use these reliable stabilizers to reconstruct our logical XX operator. It's kind of like we have now had a single surface code, but the code stabilizers are now products of X stabilizers. And the reason that this works is that these X stabilizer products still anti-commute with and detect all the Z errors on either code. And as a result, we can effectively reconstruct this logical X. So the key pattern that I want to emphasize here is that our reliable stabilizers propagate the same way as the logical operator that we're trying to predict. As a result, when we then go and measure our logical operator, we learn the right stabilizers that we need in order to decode. The 50-50 random stabilizers that I mentioned earlier are just not even necessary in order to predict our operator. And so the key question here is, can we then generalize this idea? And I think this is a good point to also pause for questions if there are any.
Actually, will it be the same if you just prepare 0, 0, -1, 1?
Yeah, the only difference there is that your XX stabilizer should be -1 instead of +1. So what you would do in effect is put all of your data qubits, for example, in -1 to start. You could do that. And it would work the same. In practice, people actually would just prepare their code in +1 and then they would prepare their code in the plus state and then apply this Pauli operator either in their mind using the fact that you can kind of reliably propagate this operator. But that's a little bit of the detail.
I guess like my question would be like, you said only the distribution of measurement, but then to what basis? You can choose different bases.
Yeah, so the key thing is that no matter in what basis we measure in, assuming that we measure in either X or Z, we should still get the right distribution of measurements. So if you prepared a different state, you would have a different distribution of measurements that you're trying to predict, but the key idea is that it should still hold. Does that make sense?
Yeah.
Awesome. Any other questions? So let's see how this idea can be generalized. So let's start by talking about how it generalizes to transversal Clifford circuits. A Clifford circuit is just a circuit where we initialize our qubits in plus or 0. We perform transversal Clifford operations such as Hadamard or CNOT that we've seen before, and then we measure in the X or Z basis. The key feature of a Clifford circuit, actually its defining property, is that Pauli operators will propagate into other Pauli operators deterministically through these states. So, for example, my plus state at initialization, which has a +1 X logical operator, will propagate deterministically through the circuit and end up as a, say, for example, a ZX logical operator. And crucially, because of this deterministic feature, this operator should also be +1 at the end of our circuit. Analogously as before, when we compute the fidelity, we just need these deterministic operators to be correct. So like in Daniel's question, we've now prepared a new state, but we just want to check that this operator is equal to +1. For these circuits, just like before, everything else is actually 50-50 random. And so we can sample from this ideal joint measurement distribution trivial and correctly. So then the question becomes, can we predict this deterministic logical operator with correlated decoding? And we'll show that the answer is yes. So to see this, let's think about what stabilizers we have reliably at the beginning of our circuit. For this plus logical qubit, our X logical operators +1, and so are our X stabilizers. When we then go ahead and do our circuit, our logical operators and stabilizers are propagating the same way as a result of the fact that the gates that we're applying are transversal. When we then measure out our qubits, we'll also gain reliable information about the XZ stabilizer product, which just as before, we can use to decode and predict the value of our XZ logical operator. So the underlying physics of what's happening here is that Clifford circuits will deterministically propagate logical Pauli operators. And these operators are kind of inherently classical, so they're not superpositions of operators. And as a result, we really only need one of our two classical codes in our repetition code to protect them at a given time, either the X stabilizers or the Z stabilizers. And crucially, the stabilizers that we need to protect this information are reliable in the basis of measures. Does this general idea make sense? Any question? Great. So let's think about decoding general logical Clifford circuits. So although we've seen that our final stabilizer measurements are reliable, it's true that when we do these gates, errors can accumulate if our circuit is very deep. And so as a result, we need to measure these noisy and slow stabilizer measurements in order to kind of extract the entropy that we generate during gates and track these physical errors through time. And in general, we'll do this by interspersing our transversal gates with these noisy stabilizer measurements. Our strategy will then be to kind of detect errors between consecutive stabilizer measurements. And we'll do this by operators that we call checks. A check is simply a product of a stabilizer measurement and its previous measurements or its future measurements. And the check will allow us to kind of detect and correct errors between different rounds of stabilizer measurements. So for example, if we just had a single logical qubit, we would compare consecutive rounds of stabilizer measurements. If they match, the product should be +1, and we have seen no error. If we had a transversal gate in between rounds, we will just simply compare a stabilizer to its forwards propagated value, because these operators should not match, and their product should be +1. And in general, we can always just track how a stabilizer propagates deterministically through these transversal Clifford gates in order to detect errors between subsequent measurements. Then, if an error occurs which anti-commutes with the stabilizer in this check, it'll flip it to -1, and we can use this information to correct it, just as before. So in practice, we'll make a data structure called the decoding hypergraph, who is going to be an input to our decoder. And basically, it's going to summarize the error model of our circuit itself. So the vertices here are checks, and the edges here are errors. So either physical errors, which will basically connect checks in space that error will flip if it occurred. And if we had a stabilizer measurement error, it will generate an error which connects the checks that it flips in time, because a measurement error will cause the stabilizer's value to change in time. Our decoder will then take in this decoding hypergraph, and it will try and find a likely error which could have produced our measured syndrome. And so with correlated decoding, by using this, we have the ability to track these physical and stabilizer measurement errors through our transversal gates. And this will enable us to just do on the order of syndrome extractions for CNO. So let's see how this looks in practice. So we consider a deep random logical Clifford circuit interspersed with stabilizer measurements. And we're going to look at one syndrome extraction round for CNO first. And in practice, we compared two decoders, one which kind of exactly finds the most likely error, and then the other one which does it approximately. And what we see is if we plot the logical error rate as a function of our physical error rate, we're able to kind of exponentially reduce logical error rate for different code distances, as long as we're below the threshold error rate for our circuit. And for these decoders, the threshold with 1 round per CNOT is kind of comparable to this 1% threshold that we saw for just a single surface code. And this is great because what it means is that instead of doing 30 rounds of stabilizer measurements per gate, we can do only 1 with a comparable threshold. Yeah, question.
Is there an intuition for understanding how this like reduction in the number of operators you need to check, because you only care about a few, leads to like an O and O of D, like you saving O of D rounds to like O of 1 round?
You said, is there any intuition in the number of operators I need to check?
I guess in practice, what happened was that because a bunch of these stabilizers are just random, you don't care about them and you only care about a subset.
Mhm.
So why does this allow you to go from O of D rounds to O of 1?
Yeah, the basic, okay, so great question. We don't need O of D rounds because at the end of the day, the first idea that you said is true, which is that we don't have to worry about certainty in our stabilizer measurements because the random ones don't matter. The reason that we're doing order of 1 rounds is just because when we do a gate, we kind of generate local errors. So we need to kind of track those errors through time, if that makes sense. So we have certainty in our stabilizers kind of at the beginning and the end. And as a result, we don't need D rounds in general, but we still kind of need to track errors that occur in the middle. Yeah. Any more questions? Yeah.
At the end, when you perform the logical comparison,
And when you perform the logical measurement.
Yeah.
So the answer is no, and it's because to perform this logical measurement, we're just going to projectively measure all the data qubits in the code. But a kind of key point is that this projective measurement is kind of almost as good as D rounds in itself, because we're learning our stabilizers to much higher accuracy. We're not using like a noisy ancilla to learn our stabilizer value. We're learning it from the data qubits themselves.
That's like the essential difference compared to the
Sorry?
like that's the essential difference compared to like certain you're learning the measurements itself.
Yeah, that's a super important point, yeah.
Could you repeat the point?
Yeah, so the essential difference, when we measure our stabilizers with a noisy ancilla, we have essentially no certainty, because any of those gates that we use to measure could have been wrong. But when we measure our stabilizers at the end of the circuit, or when we read out a logical qubit, we measure all the data qubits, and then we infer the stabilizer values from the data qubits. And this is essentially noiseless syndrome extraction. Because if you had like a measurement error on one of your data qubits, it'll actually get picked up just as a normal physical error. Yeah.
Is there some way to understand the reduction from the order D measurements to the order 1 is like entropy removal picture? Like if you're like, oh, these measurements weren't actually decreasing the entropy anyways, because they were random, and therefore there's like some argument to say, well, you know, this is a sufficient amount of measurements necessary to remove the entropy we need, and maybe there's kind of like lower bound there. Kind of builds up on this question.
I think that you're totally right. So the question was, is there kind of an entropy removal way to understand this reduction? And I think that you're absolutely right. And the idea is when I initialize my code, I actually have basically 0 entropy in my stabilizers in one basis. And it's also the basis of the logical operator that is deterministic. Then when I start doing gates, I'm generating kind of local physical errors, but my stabilizers are still pretty low entropy. And I'm just going to use noisy stabilizer measurements after that to kind of pick up this local entropy that I'm generating. And then when I measure again at the end, it's extremely low entropy and robust stabilizer measurements that I'm getting from the data qubits themselves.
Actually,
Yeah.
just like adding to my point, if we had like something compiled in that circuit, right? But we can, instead of using like a survey to merge and split the matrix,
Mhm.
we can use like a logical and Scylla and perform like CNOF with like, basically use a logical and Scylla to measure the things instead of doing Scylla. So then, you can map like a lattice surgery logical circuit to this and will work. Because here you are just measuring you're not performing the measurement with the physical, you're performing that with like a logical.
Oh, very interesting. Oh, that's a good question.
So could you repeat it?
Good question. Okay, very advanced question. The question was, suppose I have, if I understand correctly, a code made out of surface codes. And I wanted to do lattice surgery on the outer code. And I'm using transversal gates to do the operations in lattice surgery. Was that the question?
Yes.
Whoa, okay. That's a great question. Interesting. I'm not entirely, I'm thinking. I would think it is protected, but I need to think a little bit more. Not maybe I can come back to you after the talk. Any more questions? All right. So before we move on, I just want to talk about the implications for the cost of the algorithm itself. So in order to test this, in numerical simulations, we're basically fixing the physical error rate that we have and varying the number of syndrome extraction runs that we do per CMOD. And what we see is for a variety of different code distances, the logical error rate is actually minimized for doing fewer than one syndrome extraction run per CMOD, which basically just means doing multiple gates before we even go and measure our stabilizers. Then we can compute the space-time cost that we would, as a result, need in order to reach a target logical error rate. So this is just the space cost of d squared times the time cost of the algorithm itself, which depends on the number of rounds that we do per CMOD. And what we see is that this cost is again minimized if we just do roughly one run of syndrome extraction per CMOD, indicating that we get a space-time reduction by a factor of 400D for these transversal coverage. So armed with this, we then want to kind of generalize these ideas to universal computation. And it turns out we need one more ingredient in order to get universal computation where we can run any form algorithm that we want. And this is a non-Clifford magic gate. So it turns out that you cannot do these gates transversally if we have transversal Clifford gates. There's no-go theorems that prevent this, so we need another way to generate these new gates. And it turns out that it suffices to have non-Clifford magic states. So for example, a T state is an example of this. It's basically just 45-degree rotation on the Z-axis on the blocks here. And as well as feed-forward operations. So a feed-forward operation is just, during my computation, I can measure one of my logical qubits, and then I will apply an operation based on my measurement result. And for the purposes of the proof, we will assume that these T states have reliable stabilizers. And I'm happy to kind of discuss this assumption as well later in the talk. So why is it enough to have these two ingredients? The basic idea is that it allows you to do something called T-gate teleportation, which basically uses your uses your magic state, and it applies a magic T-gate to your logical qubit side by first entangling them with a transversal CNOT, measuring out the magic state in the Z basis, and then applying a transversal Clifford gate based on our measurement result. And because we're applying a logical gate based on our measurement result, we really need to actually interpret it correctly. We can't fix this very easily once we've done it. is actually a little bit of a challenging practice, how to deal with these feed forward operations. And so to see an example of this, suppose that I'm teleporting a T gate onto a plus state. I need to interpret this Z measurement reliably. And so to do that, I'm going to decode my Z stabilizers. However, if we look at how these Z stabilizers propagate back through the circuit, we realize that it requires Z stabilizers on my plus state, which unfortunately, as we mentioned earlier, are random. And so our interpretation is based on unreliable information, and this seems like it could be a major issue. But it turns out for this example that it is actually fine. And the reason is actually quite similar to before. So this measurement, if we back propagate the Z logical operators in the circuit, we see that it actually anti-commutes with our logical X operator at initialization, which is +1. And as a result, this measurement is 50-50 random. And we can, decode it by returning a random number, just as before. And so the question that this kind of begs is, can we play the same tricks as before, but now with feed forward? So we're going to use the same idea I mentioned actually at the beginning of the talk with the logical bell state. Again, the minimal requirement for fault tolerance is that we need to reproduce the ideal joint logical measurement distribution of our circuit itself. In order to do that, to reproduce this joint measurement distribution, we need to basically be able to accurately interpret new measurements conditioned on previous results. We don't need to know the stabilizers of our state necessarily in order to do this. We just need to be able to show that we can accurately sample new measurements from the ideal conditional distribution. And so how can we do this in practice? So let's consider just interpreting an arbitrary set of new measurements from a circuit that we've been doing operations on before. Now, we might have had prior feed-forward operations, but the circuit executed so far, once we apply these feed-forward Clifford operations, is still just a transversal Clifford circuit. Does that make sense, by the way? That's kind of important. Any questions? Cool. Great. So it's just a transversal Clifford circuit. And so actually we can play a lot of the same tricks as before. Actually, basically the exact same tricks. So if we have some, logical operator, a product of measurements, which when we trace it back through the circuit, commutes with all of our logical Pauli operators at initialization, because the stabilizers are also deterministically +1 in this basis, our measurement is based on reliable stabilizers, and we can just decode it as normal with correlated decoding. On the other hand, if I have a measurement which anti-commutes with the logical Pauli at initialization, it is also 50-50 random. And we can just return a random number as before. So in order to interpret new measurements, all we're going to do is just generate a complete basis of all the measurements we've done so far, which commutes with all the logical Pauli operators at initialization. And these are crucially also the deterministic or the non-random and reliable measurements that we have. And we can decode them with correlated decoding. All the other measurements by construction are 50-50 random, and we can just assign them randomly. So using this procedure, we actually show a threshold theorem that the logical error rate can be exponentially expressed with code distance D for any of a broad class of codes called quantum low density parity check codes. And these codes include very canonical class of error correction codes that we know, such as the surface code. So I'll pause here if there are any questions. The most confusing part probably. So to summarize, we've seen how transversal gates, correlated decoding, and these new strategies and understanding of fault tolerance for handling feed-forward gates and non-Clifford gates can come together and kind of give us a factor of D depth reduction in the circuit that we're interested in running for universal phone computation. And looking forward, I think that the most natural and obvious next step is to now understand what are the implications for when we actually want to run logical algorithms. And in particular, how low overhead can we actually implement an error-corrected algorithm? And there's been a lot of exciting results actually just over the past year that kind of push towards this goal. So for example, there are really new exciting results on efficient ways to generate magic, such as cultivation, which was developed by Clifford. But there's also other approaches that are quite interesting, such as distillation, which is actually recently explored experimentally by Clara. We could also combine these ideas with progress in low space overhead schemes. So there are codes that basically pack a lot of logical qubits into a few physical qubits, which could allow us to reduce the number of qubits we need for our computation. And finally, in order to realize these ideas in practice, it's really crucial to develop fast decoders that are able to keep up with the speed at which we get new measurements and need to interpret these feed-forward operations. And so I think the next question we need to ask is how much do these developments reduce the resource estimate of these algorithms? And I think that we not only need to think about experiments for the future, but it's also important to apply these techniques to experiments that we're trying to run today. And one way that we've been exploring this is tailoring to realistic experimental error models. So for example, in the atom array at Harvard, atom loss is actually a major source of error. And it's really important to correct because if you don't correct it, you will lose your entire error correcting code, which is a problem. And recent experimental developments have now shown the ability to measure if a qubit is lost when we measure the qubit state itself. And so we've been exploring, and this has been especially led by Geffen and Pablo in our group, methods to integrate this loss resolving readout in a way that allows us to do loss detection and correction with minimal overhead and logical algorithms. So this can really naturally be interfaced with syndrome extraction in order to detect loss at the same time as you measure your stabilizers. But it turns out you also get a lot of loss detection for free when we run an algorithm. For example, when we do gate teleportation and we measure our logical qubit, we naturally see which atoms were lost and can detect those losses. This in turn has really important practical implications for the performance of our experiments. So it turns out the knowledge of loss, error, and loss locations actually gives us a lot more information than Pauli errors because we can point to an atom and say this atom was lost. And this allows us to do actually much more accurate quantum error correction and decoding. So with that, I would like to acknowledge all my collaborators. So I would specifically like to acknowledge Harry, Dolev, and Chen, without which, each of them made really important developments, without which this work would not have been possible, as well as our theory collaborators, Casey, Connie, Shinka, Nadine, and Pablo. And then especially thanks to our PIs, Alex, Arthur, of course, and Misha. And I would also like to thank the broader Amory team at Harvard, our theory PIs, and theory students here at Harvard as well. And with that, I'm happy to take any last questions.
Well, thank you for a very interesting talk, and there were a lot of questions, but maybe there are a few more. Leon.
I have an intuition. I don't know whether it is correct.
Mhm.
It's like that we reduce the DRAMs to one row because like we always keep track all of those Pauli propagation along this stabilizer. And we do correction at the end, so we don't need to do that at each time we measure those stabilizers.
Yeah, that's exactly true. We don't need to correct our errors live, is your point. we can correct them kind of in post-processing. Yeah, that's exactly true.
Thanks for the awesome talk. I was just wondering, here's like a conceptual question, like, so, obviously we made a lot of progress in the surface code and like the last, few years, surface code been really useful, but the other field of PC code seem promising. And like kind of near-ish term, do you see a shift from like surface code being the top dog to something promising kind of upcoming? Like, are any of these other good LDPC codes seem like there's big enough qubits who would actually want to use them, or is it really going to be the surface codes era for a little while longer?
I think it's gonna be a mixture of both. I think that these high rate codes are super cool. And they absolutely allow you to save resources, at least in terms of the number of physical qubits that you need. The real question is just for a given computation, does it make more sense to use these high rate codes where sometimes I have a little bit more limited gate set that I can do transversally? Or does it make sense to just use the service code where I can implement any Clifford circuit I want transversally? Yeah.
So I wonder, like, if we just use error detection instead of correction, what's like, does this correlated decoding give us like better results, or? Because, okay, so like one arrow can spread to like a multiple qubit poly arrow. But then if we are just doing detection, yeah, I don't, like, it's essentially the same.
That's a good question.
Because in the distillation factory, for example, you say like, okay, I just, it's also just some Clifford operation after or like transversal operation after preparing T states, right?
Yeah,
And it's like everything.
I think that
Could you repeat?
the question was, do we gain anything with these techniques when we do error correction or error detection? I think that the gains would probably be minimal, but the reason that people don't normally think about doing error detection is just that it's very unscalable. So a single error and you're going to throw away your shot. So if you want to do a big circuit, it's not super scalable in that sense.
Are there any questions online? Don't see any. So thank you again, Maddie, for a really exciting talk, and we're looking forward to more implementation.